Hello everyone. In continuation with the Thinking Machine series, I would like to introduce another point of view for building thinking machines. You should look at my earlier video series to get better context and continuity, which will help you get into learning groove. Building thinking machines using Neuro-Symbolic AI, NSI, means developing systems that can both perceive the world like humans via neural networks and reason about it like humans via symbolic logic. We are going to delve into one of the most exciting frontiers in artificial intelligence, Neuro-Symbolic AI. This field promises to bridge the gap between human-like reasoning and the powerful pattern recognition capabilities of modern AI, ultimately bringing us closer to building true thinking machines. Neuro-Symbolic AI represents a significant step forward on the long road to building truly thinking machines. By synergistically combining the power of data-driven learning with the rigor of symbolic reasoning, we are moving closer to creating AI systems that can not only perceive and process information but also understand, reason, and interact with the world in a more human-like and intelligent manner. The future of AI is undoubtedly a hybrid one. While powerful individually, both approaches have limitations. Neural networks, for all their prowess, often act as black boxes, lacking transparency and interpretability. They struggle with common-sense reasoning, learning from few examples, and adapting to truly novel situations outside their training data. Symbolic AI, conversely, can be brittle, struggling with noisy or incomplete data, and often requires painstaking manual engineering of knowledge bases, which can be difficult to scale. The core principles of Neuro-Symbolic AI revolve around a few key ideas. Firstly, the ability to learn rich representations and patterns from raw data, much like neural networks. Secondly, to leverage explicit knowledge and symbolic reasoning for structured problem solving. And thirdly, and critically, to enable a degree of explainability and interpretability in the system's decisions, moving beyond the black box problem. Neuro-Symbolic AI employs various hybrid architectures. One common approach is to use neural networks as perceivers that extract symbols or high-level features from raw data. These extracted symbols then populate a symbolic knowledge base, which is used by a reasoning engine to perform logical inference, planning, or decision-making. The results of the symbolic reasoning can then, in turn, be used to guide or constrain the neural network's learning. Another approach is neural-guided symbolic reasoning. Here, a neural network isn't just extracting symbols, but actively guiding the symbolic reasoning process. For example, a neural network might learn to select the most relevant rules from a large knowledge base for a given query, or even learn to generate new logical constraints. This allows the neural network's pattern recognition abilities to inform and enhance the efficiency and effectiveness of symbolic reasoning. Conversely, symbolic knowledge can be used to guide and constrain neural network learning. Imagine explicitly encoding common-sense facts or domain-specific rules into the training objective of a neural network. This can improve data efficiency, enhance robustness, and lead to more interpretable models. For instance, if we know that all birds can fly, a symbolic rule, we can incorporate this into a visual recognition system, preventing it from classifying a bird as flightless, even with limited examples. This is where Neuro-Symbolic AI steps in. It's an emerging paradigm that seeks to combine the strengths of both neural networks and symbolic AI, creating systems that are not only capable of learning from data but also reasoning, explaining their decisions, and incorporating prior knowledge. The goal is to build a bridge between these two powerful paradigms, enabling us to overcome their individual limitations. While promising, Neuro-Symbolic AI is still an active area of research. Challenges include effectively integrating and translating information between neural and symbolic representations, scaling these hybrid systems to real-world complexity, and developing robust evaluation methodologies. Future directions involve exploring more seamless integration methods, developing new formalisms for knowledge representation that are amenable to neural learning, and pushing the boundaries of truly robust and explainable AI. I will further share the more insights and details about how to build thinking machines and underlying principles in my coming video series. Please subscribe my channel and like the video so that I can bring interesting insights and updates on thinking machines.